Hello everyone, welcome to Tactica Imperialis and to today's video. Today is going to be another of my Tactica Tutorialis science lesson videos, and we're going to be doing a GCSE triple science physics topic today. So if you're an A-level physicist, want to be, or a triple physicist at the moment, this is for you because this comes up a lot at A-level physics as well. In fact, having taught it at A-level physics, they're almost exact parallels to each other. So what we're going to look at today is impulse, impact, and car safety. This is two lessons that I did for my current training school that I've cut together into one mega lesson for you guys because it flows quite nicely from one to the other. In fact, there's supposed to be one lesson on the spec, but we separated them out and now I'm putting them back together again. So, the lesson's going to work the same way as my Newton's Laws lesson. In the description are a series of videos which are unlisted as the solutions to the various exercises that we are doing. So there's a couple of writing exercises and there's a big calculations exercise in the middle, and all of those exercises are linked in the description. But what's this lesson actually about? Well, impulse and impact are all to do with changes in momentum. Now, we haven't done a lesson on momentum on the channel to this point, but hopefully what we do at the start will give you what you need to at least get an idea of what's going on. I'm not going to be asking you to calculate a lot involving momentum. You're just going to use momentum as a number rather than as a formula to then derive other things, but I will give it to you at the start of the lesson, and if you feel you need to go and look up a bit more about momentum before you start, that is absolutely fine as well. Towards the end, we're going to have a little practical demonstration as well, and it may be the finest 6 or 7 minutes of video footage I have ever put to film, especially for this lockdown period. I had so much fun filming this little practical that I had to show it off to you guys. It was a lot of fun to do, and I really hope that it gets across the points that we're making throughout the lesson. So, if you hear any references to online resources and companion PowerPoints, don't worry, that was for the class that have seen the lesson now. This is for you. So don't worry, you won't have them, but you don't need them. They're identical to what you've got here. And I wish you the best of luck. I hope you enjoy this, and I really hope you enjoy the little practical at the end. So, without further ado, let's take a look at impulse, impact, and car safety. Let's begin. So, here is your first task for today. A little starter activity just to get your brains ticking. What I'd like you to do in your books is write down the 3 equations that I've asked for on this board here. The first is Newton's second law. So you need to recall what Newton's second law is and write down the formula for it. Second, I'd like you to write down the formula for acceleration. Now, there are 2 ways you can write that one down. I'll leave it up to you to how you want to do it. And the third one from last week, I'd like you to write down the formula for momentum, please. Lay it out something like this. So 1 line is Newton's second law, 1 line is acceleration, 1 line is momentum. Write them down because you're going to use these equations as part of today's lesson. Try and do this without referring back to your notes. If you need to go back to your notes, do so. And if you need to check the solutions, then go and look at the solutions video because I'm not going to go through it here. I'm going to assume that you have done that. So, without further ado, let's move on. Do this, check the solutions video, come back here, and we'll talk about how all of this ties together. So, let's talk all about impulse as a concept and link everything we've done so far together. So the first thing is Newton's second law. I'm going to start from Newton's second law, which you should have from the starter as F equals ma. Like I say, iconic formula, F equals ma, Newton's second law. However, from the starter, we know we can write acceleration slightly differently. We know that we can say that acceleration A is equal to delta V over T. So we can now rewrite Newton's second law as F equals m delta V divided by T. I'm going to write it like that. However, we've also seen the momentum formula. Momentum P is equal to mv. But we could therefore say change in momentum, that's not how you spell it,
change in momentum, delta P, this is a slightly different way of writing it, delta P, you could say, because generally the mass of an object doesn't change, is equal to m delta V, because the mass is usually a constant. So we can now plug this into here and say that F is equal to delta P over, I'm going to write here, delta T. Now, remember what I said at the start of solutions. Delta T and T, in this context, it's a bit of a squaring the circle problem, but they mean the same thing. So what that means is, and this is the formula that you need to take away from today, force equals change in momentum divided by time. That is the formula. The force on an object when it changes speed and has a crash is the change in the object's momentum divided by the time taken for that collision to happen. There'll be a similar version of this in the PowerPoint if you want some slightly longer notes than this, but this is what you need to know. The force, the impact force, we quite often call it, is equal to the change in momentum of an object divided by the time taken for that change in momentum to happen. So those are the two big things. All of this is a quick derivation that you should take down. So pause the video and do that. And now I'm going to make a couple of short notes for you that I also want you to take down before we do some exercises. So here are the key notes that I'd like you to take down from today's lesson. The bits in blue you don't have to take, but they are useful to have, I think. So when an object is in a collision, that could be a car crashing into a wall, that could be a cricket ball being hit by a bat, it could be any number of things where something bangs into something else, a collision happens, there is a change in momentum. You're going to do a couple of questions about this in a couple of minutes, but there are many examples where the momentum can do a lot, but there is a change regardless. And that change in momentum causes a force to be applied to the object. And we call that force the impact. And if we go back to the formula, we saw that the force was equal to the change in momentum divided by the time. So if you were able to increase the time, and I will show this in the practical later, then by increasing the time for a constant change in momentum, the force becomes smaller. So say the change in momentum was 1. If the time was 1, the force would be 1 because it's 1 divided by 1. But if the time was 2, the force would be 0.5 because it's 1 divided by 2 now. That would therefore mean that the force is decreased. This is very important, for example, with car safety, which is going to be our next lesson. Because if you can get that impact force down, the lower you can get it, the safer the collision is. So if you're sat in a car, that you want the collision to last as long as possible. You want it to take as long as possible for you, the person, to stop so that the force on you is reduced. Obviously, there are times when you want more force, for example, the cricket bat example I mentioned before, but it is a really important concept that as the time goes up, the force goes down. Right, I'm going to now rub this off and we're going to do a very short couple of examples about change in momentum, and then you're going to do a couple of questions all on your own, and there'll be solutions for that in a separate video. So for our first example, we have a brick moving at 5 meters per second, and it's going to crash into a wall and stop. We need to work out what the change in momentum is. So we need to work out delta P, and it is equal to m delta V. The mass of the brick, by the way, is going to be 1 kilogram. We're going to keep it simple and call it 1 kilogram. So we need to say delta V is equal to m v minus u. That's typically how we do it. Final velocity, take away initial velocity. So what do we know? We know the initial velocity was 5 meters per second. And we know that the brick stops, so its final velocity is 0 meters per second. So delta P equals 1 times 0 minus 5 equals minus 5 kilogram meters per second. Yes, you can have negatives. That's not come out very well. I'm going to write that in a different color. Minus 5 kilogram meters per second. You are allowed to have negative changes in momentum, because if you only had positive changes in momentum, then, well, things would only ever get faster, and that doesn't make sense. To stop things, you have to reduce their velocity, and so you end up with a negative change in momentum. Now, normally, if you were then to calculate the force, then you would have to talk about it in terms of vectors to say that the force was minus force in the direction of motion, so it was a positive force in the opposite direction. Because you could say, if the brick was moving right, then the change in momentum is minus 5 to the right. However, you could equally say that it is 5 to the left, because we're talking about vectors here, so we have to specify the direction. I haven't here to simplify it, just pointing out you can get negatives. So our second and final example, before I let you loose on the questions, is as follows. We have a ball moving at 3 meters per second to the right, has a mass of 500 grams, and it is kicked and now moves 4 meters per second to the left. What is the change in momentum? So some of you might be tempted to go delta P equals mass, final velocity is 4, initial velocity is 3, so it's 0.5, right? Wrong. I know the temptation, but wrong. You have to consider the direction. Think of it like a number line if it helps. So at the moment, the ball is moving 3 meters per second in that direction. It's then going to get booted and is now going to go back the other way. So the change in velocity, so delta V equals, so the final velocity is 4 left, take away 3 to the right. But we now need to define, and this is something that's going to be quite awkward, our positive direction. So we're going to say, for the sake of argument, that right is positive. Right equals positive. So now, if you're moving to the left, that is equivalent to moving with negative velocity to the right. So if you think about it like this, so taking 1 step to the right is plus 1. Taking 1 step to the left is minus 1. So if it's moving at 4 meters per second to the left, its velocity is minus 4 meters per second to the right. So, get my other pen out. We can therefore say delta V is minus 4 to the right, minus 3 to the right, because both of them are now treated as moving right. So there's your V minus U that we had before. And therefore, our delta P equals M delta V equals 0.5, because 500 grams is 0.5 kilograms, times by minus 7 equals minus 3.5 kilogram meters per second to the right. Or you could do it the other way. You could say that left is positive, and therefore you have 4. So if I do that the other way, if I say left is positive, I would have plus 4, take away minus 3, minus take away a minus is a plus, so I would have plus 7 there, and plus 3.5 kilogram meters per second to the left. It all depends on the direction. This is also what I was talking about before. Right, on the screen now are going to appear a couple of questions from the textbook that talk about change in momentum and also about the force equation that I gave you earlier. Have a go at them. The solutions video is going to be separate to this one, not going to show them here. Do them, practice them, get the solutions off the other video, then come back here and we're going to have a little practical to finish off.
Alright, so we are roughly at the halfway point of the video. I've just finished the first of the two lessons, or at least the parts of it that you need to see. And we're ready to move on now to the car safety section. Before we do that, or before you do that, make sure to take this opportunity, pause the video, and check and go back and do the exercises and the write-ups and check the solutions for anything that you need to do. All links are in the description, of course. And then when you're ready, you can unpause the video and start the second section. Now, it's going to say in the corner that there's a starter activity. That's because, as I say, this was a second lesson. It is essentially a recap of what we've just done. So you don't need to treat it as a separate lesson. It's just not a new starter. It's just a recap to connect the two lessons together since it was done over a couple of days for the students there. One thing I will ask you to put in your notes, which I think I do talk about in the solutions to the second starter, but not everyone watches those. Force is also defined as the rate of change of momentum. It's quite a common term on GCSE and A-level papers to see rate of change of momentum written down or expected to be written down in wordier answers. What that means is essentially the force, the impact if you're at A-level, or the rate of change of momentum, particularly at GCSE. That's a phrase that I would like you to get down. I don't stress it very much in the first half of this video, but I do try and use it more in the second half. So just want to make that clear in this little interlude. So pause up, do your notes, do your calculations, check your solutions, and when you're ready, let's get started with car safety.
So, to get us started off today, we need to just make sure we're all on the same page when it comes to impulse of a force. Just to make sure that we know the basics before we get into the details today. Now, if you need to go back and watch the previous video, the previous lesson that I did on impulse of a force, in order to help you all complete those exercises, please feel free to do so. But what I'd like you to do, pause the video, solutions in the description or in the Google Classroom post, is I would like you to write the word equation that I gave you last lesson. I would like you to write the symbol equation as well. And then I'd like you to complete the following sentence, which is also going to be on my companion PowerPoint. If we increase the time for a collision to happen, what happens? So complete that sentence. If we increase the time for a collision to happen, what happens? So those are your three tasks. Now, normally I'd say check the solutions if you need them and so on and so forth. But for this one instance, I would absolutely mandate that you go watch that solutions video. I'm not putting it in here for the sake of levity with the video and speeding things along, but go watch it as there's a very important point in it that I need to make that I didn't make clear enough last lesson. So have a go at this, go watch the solutions video, and then come back here and we'll talk all about car safety. All right, let's talk about car safety, shall we? Now, if you want to have a go at filling in these gaps before I start going through this, then absolutely you are within your right to do that. Pause the video, have a go. I think it would be worth you trying to think this through before I talk it through, so that way you'll be better able to understand what I'm rambling on about. So have a go at that. Pause the video, and then we're going to talk through what I mean here. So, in a car crash, there's a change in momentum. I think we can all agree on that. Our car, whatever it is, we'll say it's this rubber, is driving along, and bang, that's a wall. Or bang, that's another car, and it goes off to one side. Either way, the momentum of the car changes. Either it comes to a dead stop, or possibly it's deflected off and some of its momentum is reduced in, say, that direction because it's been passed on to this other object. Either way, the momentum changes in some way. Now, cars are pretty fast. So, for example, if you're driving at 60 miles an hour, you're approximately doing, I think, 100 kilometers per hour. I think that's the rough conversion, which, if you were to work it out, is 100,000 divided by 3,600. 100 over 3 and a bit is about 30-ish. So you're doing about 30 meters per second if you're going at 60 miles an hour. You can look up the exact number for yourself. I've just done that off the top of my head. But therefore, we can say, because cars are also quite heavy, like most of them are in the region of a ton, which is, or more, which is 1,000 kilograms, then we say that there is a very large change in momentum, or a high change in momentum, because high mass and usually high velocity. Now, we want to minimize the rate of change of momentum. Now, rate of change of momentum is what I defined to you in the starter solutions video, and that is the force, i.e. the force. We want to minimize the impact force of the collision. We've got a huge change in momentum. We can't do anything about that because our car's just, it is what it is, and it's traveling at the speed or velocity it's traveling at. We can't really fix that, but we need to get that force down. Partly to minimize the damage to the car, so we hopefully don't have to write it off, but primarily to protect ourselves, because I hate to say it, despite what everyone seems to think, we're not that tough. We're quite soft. We're quite squishy as humans, and we break easily, let's be honest. So we need to protect ourselves. And the way we do this is by increasing, this is something we've talked about several times now over this lesson and the last one, by increasing the time for the car, bracket, or us, close bracket, to stop. Because if we can make the collision last as long as we can, that force is going to come down, 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 and thus the damage and the risk comes down with it. Now, the very obvious implication of this, and something that's very easy to assume, I'm just going to put that S a bit nearer to the T so you know it's part of that word. You assume that the force is applied to the car, obviously, and it's also applied to us. Now, that's actually not quite the case. There's a slight difference going on, and you see this every time you see a car get its brakes slammed on. So if you've ever been in the car and you've had to slam the brakes on for a red light, or whoever was driving had to slam the brakes on for a red light, or because some Egypt cut them up, it's happened to me and my family more than enough times, you've had to slam the brakes. And you've probably felt yourself lurch forward a bit, sort of get thrown almost forwards against your will by the slamming on of the brakes, and you've been caught by your seatbelt, usually, so you don't whack your head on the nearest seat/airbag. And that is because, and I can tell you this because, well, this is stuff that we only do for triple, and I trust that you can get your head around this, is that you are not subject to the force that the car is. I know, that's weird, but bear with me. So, the car has hit the wall. You are inside the car, but you are not attached to the car. You are not part of the car. And as a result, you, by Newton's first law, have, well, not by Newton's first law, you have not had that force applied to you yet. Because you are sort of a floating object. Imagine you don't have your seatbelt on. You're sort of a floating object sat within the car. So you are moving with the car and have a velocity and a momentum, but you are not subject to that force right away because you haven't hit the wall yet. So what happens when the car crashes is that its momentum starts to change and is reduced. Your momentum sat within the car does not, and you carry on going forwards because Newton's first law says so. You are not subject to any force at this time, so your state of motion cannot change. You keep going forwards until you bang into something, and then you slow down. Usually that's the seatbelt, or if you're really unlucky, it's the front seat. It usually isn't the front seat, it's usually your seatbelt, unless you've forgot to put your seatbelt on or your seatbelt breaks. That very rarely happens. So generally, you don't stop just because the car has. And that's why some people in very unfortunate car accidents or collisions you might have seen in movies go out the windscreen, because they are not subject to the force that the car is, because they're not the car. But if we can reduce the force and increase the time for the momentum to change, that throw forward effect is reduced. So for example, you slam the brakes on, you get thrown forwards. You gently ease on the brakes and slow down slowly, you don't get thrown half as much, and sometimes you don't even feel that pull forward at all. And that's because of increasing the stopping time. In total, that's all it is. It's a change in the stopping time, is decreasing all those forces and thus allowing the momentum to change in such a way that you don't notice. So that's just an aside. You don't need to write that down. I realize I've rambled on a little bit, but that I wanted to tell you that, and it's going to be very important for the practical that we're going to do in a moment. So, welcome to the lab for today's lesson. I know, it's a bit weird, bear with me, I've only got so many resources in my flat. So, what we're going to do today is we're going to simulate an NCAP car crash, and we're going to do it in order to demonstrate some car safety features and the impact that they can have on, well, impact force. To do that, we're going to need a car, a wall, and a crash test dummy. We have a wall. This box is going to double as our car, and our crash test dummy is going to be this guy. This is Steve. And Steve doesn't really get this whole car safety lark, and unfortunately he's now going to find out in the least fun way possible. So, how this experiment's going to work? Steve is going to sit in the back seat of the car, just there. And Steve is going to be crashed into this wall. The whole car is, in fact. I'm going to push the car at a constant speed and attempt to, at the same speed, crash it into the wall a few times. And what we're going to investigate is the displacement of Steve. Because when the car hits the wall, its momentum changes and there is a force applied, because force is rate of change of momentum. However, Steve hasn't hit the wall yet, so there is no force on him. So by Newton's first law, an object cannot change its state of motion unless a force acts on it, Steve is going to keep going forwards. And you'll know this yourself. If you ever been in a car when the brakes have been slammed on and you've lurched forward, that's the same thing. That's Newton's first law in action. And that's what's going to happen to Steve. But if the impact force is reduced, then there is going to be more time where the velocity of Steve and the car is similar, because the car is going to take longer to slow down, meaning Steve's speed relative to it is going to be closer, meaning that Steve will not travel as far, which means that could be the difference between Steve ending up in the front seat and Steve ending up in the wall. And we're going to investigate that. And we're going to do two crashes. So the first crash is going to be exactly as you see it here. And with this red pen, I'm going to draw where Steve ends up. So I'm just going to draw a red line wherever Steve ends up. The second time we do it, we're going to use one of these. Yes, it's a yogurt packet, bear with me. It's going to double for us as a crumple zone. You can see it's got that bit of squidge to it, and I'm going to stick that to the front of the car. And then near to the same speed as possible as I can, I'm going to crash it into the wall again. And with this green pen, we're going to draw where Steve ends up. And we'll compare the two. Now, from your own studies in this lesson so far, you should already be able to predict what's going to happen. But please feel free to do so now, since I'm sure you'll be intrigued. And then when you're ready, we're going to have a go. We're going to see what happens in this car crash. So, first go, red pen. No crumple zone. I'm going to try and time this to go at the exact same speed. If I get it wrong, bear with me. I'm going to go quite fast to demonstrate it. So 3, 2,
1. Okay, I'm going to try that one more time because I think I took the brakes off because I was scared about crashing it. 3, 2, 1. As you can see, hopefully, Steve hit the wall and bounced off. So, on the box, I'm going to draw a red line right at the end because Steve ended up flying out of the car and hit the wall. Now, let's do the same with our crumple zone. So we're going to attach the crumple zone with some double-sided sticky tape to the front and get the green pen ready. So let's do it again. 3, 2, 1. So let's draw that. So that was about there. So let's bring the box up so you can have a look at what I've just drawn. So without the crumple zone, Steve ended up all the way out the front of the car. Now, I tried to get the same speed the second time, but with the crumple zone, Steve ended up not that far forward. Probably, if that's the back seat, maybe clunked his head on the front seat, probably at worst. And that was purely this entire difference. And bear in mind, Steve bounced off the wall, so Steve would have probably ended up somewhere over here, was down to the crumple zone. Because the crumple zone increased the impact time and thus decreased the rate at which the momentum of the car was reduced, therefore reducing the force, allowing Steve to travel less distance before the car came to a stop. This right here is the power of car safety features. Like, just with a crumple zone, Steve has gone from out the front windscreen to barely hitting the front seat. If Steve had got a seatbelt, which, for example, I could have simulated by some blue tack underneath here to hold him in place even more, he'd have barely moved at all. If I'd have had some airbags, I know the back seats don't really have airbags, but if I'd have been able to simulate that with a little cushion up here, then he would have moved even less distance. And that's the power of it. I know it's not a perfect practical one. I've done this at school before. I've done this with trolleys and masses and pulleys and made it a perfectly fair test, but I had to improvise. But there you go. That is the power of a crumple zone. So let's wrap up the lesson, shall we? Right, there we go. That is the end of today's lesson, or lessons you could say, because they were 2 lessons stitched together. I hope that flowed reasonably well. I did try and sort it out in the edit so that it didn't feel too much like 2 lessons just jammed together for no good reason. But I hope that you can see how those 2 topics are connected together, how the ideas we established in the first half with impulse and impact time will connect together to car safety features and the practical that we did at the end. Now, I should stress that if you're an A-level student who decided to watch this video, impulse and impact is the terminology that you need to know. Impulse for change in momentum and impact for the force. If you're at GCSE level, we don't actually use those terms. Change in momentum and force is all you will need because that's what's on the formula sheets at GCSE. I know it's a little bit weird, but that's why they were in blue and not to be taken down for the GCSE students. It was more for the A-level students in the room. So, I hope you found the lesson enjoyable and I hope you found it informative. I certainly had a lot of fun making it and I still believe that practical is the finest thing I will ever film. So, what our next lesson is going to be, I'm actually not sure. I am still intending to do the gas laws lessons from a previous commenter request, but let's just say the ideal gas equation and all of the kinetics that go into that theory it's going to take me a bit of time to work through. I'm probably going to need several runs through it just to get my head around the theory again because I haven't seen it in a few years. But I will try and get a lesson out on the gas laws at A-level and I'll certainly get one out of GCSE at some point. But of course, I'm always open to taking requests. This is my series, but it's done to help teach you guys and your younger ones if they're at school. So do let me know your suggestions for topics you would like me to cover. From physics, maybe some lower school science as well. I'm open to ideas. Do let me know. So, thank you very much for watching. This has been Tactica Imperialis, and this has been my Tactica Tutorialis lesson on impulse, impact, and car safety. Thank you very much for watching, and I'll see you all again. Bye for now.